Okay, so today we're going to talk about finding derivatives of polynomial and exponential functions. And the good news here is in chapter 2, we talked about finding derivatives by using the definition of the derivative. So the good news from this chapter on is we are going to find these shortcuts, or we're going to use the definition of a derivative to prove how we could find derivatives of polynomials without having to do it the extensive way that we've always done it. So basically, our goal here is to simplify finding derivatives. So we could say last chapter we learned how to find derivatives using the definition of the derivative. And if you remember, and I'm sure you do because we don't learn to forget, right? But if you remember, the derivative we defined, the derivative of x in last chapter, we defined as the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so this is by definition. So what we're going to do now is we're actually going to learn the shortcuts, which I'm sure some of you will be excited about. But keep in mind that in this class from now on, when I tell you that I want you to find the derivative of a function using the definition of a derivative, you have no choice but to do it this way. Okay. Now, if I don't specify how I want you to find the derivative, then you could use the shortcut at any point. So of course, we care more about using the shortcut to do more interesting things in this class. So we all know how to use the definition of the derivative, or at least I would hope we do. And so these shortcuts are going to help us do more interesting things in this class and things that are more relevant to kind of what's involved in the real world. So let's start off by the most basic derivative, which is the derivative of a constant function. So the derivative of a constant function. So we could say the following, the derivative with respect to x. If you remember this notation, last chapter I said d dx means you're finding the derivative with respect to x. So x is my independent variable. So this tells me something like this. If I look at this, see, what am I treating c as? C is treated as a constant because of this d dx. This is telling you that x is your variable. So you're finding the derivative with respect to x. Now, just one side note, if I'd written, and you don't have to put this in your notes, but if I had written d dc of c, this is saying a different story here, right? Because what we're saying is you're finding the derivative with respect to c. So c is my variable. So here, I can't treat c as a constant because clearly it's not. This is telling me what my variable is. So coming back to this, see, we're finding the derivative with respect to x of a constant, which this is always going to equal to 0. So what is it that we're basically saying? We're saying that the derivative of any constant is always going to equal to 0. And see, the question could be, well, how do we know that's true? How do we prove it? And guess how we prove it? We prove it this way. So think of it this way. If I were to say, here's kind of like the proof of it. If f of x equals to c, let's find f prime of c. Then, by definition, f prime of x would be what? The limit as h approaches 0 of f of x plus h minus f of x all over h. What does that become? The limit as h approaches 0. What would f of x plus h be? Well, if I plug in x plus h, there's nothing for me to plug in. It'll just be c minus c all over h. And what's c minus c? That just becomes limit as h approaches 0 of 0 over h, which of course that is 0. So notice how we're saying I don't care what this is, as long as it's any constant function, the derivative of any constant is always 0. Okay, so moving on to the power rule. So here's what the power rule says. If n is any real number, then the derivative with respect to x of x to the power of n. So notice what we're doing here. We're saying if you have any variable to any power of any real number, the derivative of this is equivalent to the same thing as n times x to the power of n minus 1. So basically, once again, how do we come up with this shortcut? We use the definition of a derivative. So I'm not going to prove all of these by using the definition of a derivative, but to show how the derivative of x to the power of n is the same thing as n times x to the power of n minus 1, you'd use the definition of a derivative. So let's see what this is saying. All this is saying is if you ever have something x to the power of a real number, the derivative of that would be you just bring this n, put it out front, right? But basically that's what we did. We brought the n out front, and you subtract 1 from the power. So it's basically this n, this power becomes the coefficient of x, and then you subtract 1 from the power. And that's how you find the derivative of some kind of a power function, or anything of the form x to the power of some real number. So let's look at our first example. Find the derivative of f of x equals to x times the cube root of x plus x squared minus 2. Let me move this up so you could see it. So once again, this is the cube root of x, okay? So we want to find the derivative of this. So what you notice is when I'm finding the derivative here, I could find the derivative of each part separately. Now look, this we already talked about. We know that the derivative of constant is always going to be 0. This x squared, if you look at it, looks kind of like that. So this we know how to find the derivative of. We could use the power rule shortcut. However, if you look at this is a product right now. It's like x times the cube root of x. So this right now looks a little complicated. But here's the trick. Anytime you're asked to find derivatives and you see roots, we're better off writing them in terms of powers because that just simplifies everything. So before I find the derivative of this, I kind of want to simplify this a little bit just to kind of make it easier for me to work with. So if I rewrite this, what would this be? This will be the same thing as x times x to the 1/3, because the cube root of x is just x to the 1/3 plus x squared minus 2. And see, I'm not even ready to find the derivative just yet, because what I could do is I could multiply these together. And what is it that we know? When we multiply the same bases together, we add the exponents, which, what does that mean? F of x becomes x to the 1 plus 1/3 is 4/3 plus x squared minus 2. Now look at what this looks like. This actually looks like I could use the power rule because it's x to some power. So now I could find a derivative. So I haven't found a derivative. Notice how all this work I've done, I haven't even answered the question. But let's continue. Let's finish this off. So f prime of x would be what? This is the power rule. So what do? I grab the 4/3, move it out front. So it'll be 4/3 x, and then subtract 1 from 4/3. And if I subtract 1 from 4/3, that leaves me with 1/3 plus, then bring the 2 down. This is the power rule again, which would be 2x, and then minus the derivative of a constant is 0, so that just zeroes out. So all I'm left with is f prime is 4/3 x to the 1/3 plus 2x. Okay, so that's our first example. Now let's move on to some rules of derivatives. Okay, and these are some nice rules that we could use. So the first one is called the constant multiple rule, which says the following. It says, if C is a constant and F is a differentiable, function, then the following is true. So here's what, before we go on, c is just some constant, and f is a differentiable function. Remember, what does it mean if a function is differentiable? That means the derivative of f exists. So if you could find the derivative of f and c is a constant, then here's what we could say. We could say the derivative with respect to x of c times f of x is the same thing as saying c times the derivative with respect to x of f of x. So in other words, it's saying constants kind of just tag along. It doesn't really affect the derivative that you're finding of a function, unless if it's just a constant by itself, because the derivative of any constant is 0. But all we're saying is constants always just tag along. So for example, one thing I could say is, if I were to say find the derivative of 3x to the fourth. See, the question is, what happens to this 3 when I find the derivative of this? Well, nothing really. It just tags along. It's kind of like saying, what's the derivative of x to the fourth? And then the 3 is just there, so it's kind of like tagging along. So if this is f of x, then what could I do? I could say f prime of x is the same thing as what? 4 times 3x cubed. So what happened? I still brought this 4 down, but I didn't really care much for the 3. The 3 kind of just tagged along. So I still used the power rule. I brought the 4 down, and then I subtracted 1 from the 4, which gave me this 3. But then what happens to this 3? Well, this 3 is going to multiply to that 4, which becomes 12x to the third. So basically what this is saying is, whenever you have a constant and you're trying in front of your function that you're finding the derivative of, you could kind of let the constant tag along. Find the derivative of whatever this is, and then multiply it by the constant. Okay, so let's move on to the other rules. So the sum rule, we kind of used the sum rule already in example 1. So this is pretty straightforward. And then the difference rule also applies as well. So in fact, in example 1, not only did we use the sum rule, we also used the difference rule. So the sum rule just says the following. It says if f and g are both differentiable, then the derivative with respect to x of f of x plus g of x is the same thing as, so this is saying we want to find the derivative of these guys with respect to x of f plus g. That's the same thing as saying find the derivative of each of these separately and then add them up. So you could say find the derivative with respect to x of f of x plus the derivative with respect to x of g of x. So if you think about it, in example 1, we kind of did that, right? Didn't we? We split it up, we found a derivative of each separately, and then we put them together. So that's basically what this is saying. And of course, the difference rule says the same thing, except it's just a difference. We're subtracting. So let's write out the difference rule. And here's what the difference rule says itself. If f and g are both differentiable, then the derivative with respect to x of f of x minus g of x is the same thing as the derivative with respect to x of f of x minus finding the derivative with respect to x of g of x. So this is saying the same thing. Find the derivative separately and then take the difference. Okay, so pretty much says the same thing as before. So now, before we finish up this section, I want to talk about exponential functions. And we'll finish up this section by talking about what the shortcut of an exponential function is. But before we do that, we'll also define the number e, because that's something you've seen before. I don't know if you've ever had it defined or not, but we will define it here anyway. So we've noticed that in the past, you know, even if you've tried, we could say that, look, we've noticed that when trying to find the derivative of exponential functions using, oops, let's write it down here, using the definition of derivative, this gave us some problems. Gave us some problems. Okay, so I'm putting the problems in quotation just because we would have to manipulate it in a certain way. So the h in the denominator, if you remember, doesn't cancel out as simply as certain other problems. So the question is, how do we kind of take that into consideration? So we could say, look, take, for example, y equals e to the x. See, by definition, what do we get here? We get, and let's be specific, by definition of derivatives, we have y prime equals to what? The limit as h approaches 0 of f of x plus h minus f of x all over h, which yields limit as h approaches 0 of e to the x plus h minus e to the x all over h, which here right away you could notice there are some problems, quote unquote, right? Because how am I going to cancel this h out? So what we could do, however, is we could say, look, what am I doing here? This limit only cares about h. See, it's saying h approaches 0. So the x isn't affected by this h approaching 0, is it? So what we notice is we could say, wait a minute, since x isn't affected by this limit, and we have our properties of limits, we can grab whatever that's not affected by this limit and put it out front, because this limit is saying, I care about h. H is changing. You cannot mess with h. You can't grab h and move it out. So what I could do is, I could grab this and factor out the e to the x, which then gives me limit as h approaches 0. And if I factor out an e to the x from this, what do I get? I get e to the h minus 1 all over h. And see, once again, what we notice is we can't cancel out what's going on with this limit here as h approaches 0. I can't cancel the h out. So probably the best thing to do here is let's make a table and see what happens with this. So if I were to create a table here, let me get rid of these guys. And we're going to say, what do we want? We want e to the h, but I'm just going to call it, using my calculator, it'll be e to the x minus 1 all over x. So instead of h, I'm putting x. So what I'm going to do is I'm going to get x closer and closer to 0, and let's see what happens to this. So if I go to my table, and if I plug in 0.1, what do I get? I get 1.0517. What if I do 0.01, 0.001? What do you notice? As I'm getting closer to 0 from the right side, this is getting closer to 1. Now let's try it from the left side. Negative 0.1, I get 0.95. Negative 0.001, I get negative 0.995. So we could start seeing that it gets closer and closer to 1. So what's the good news here? This basically becomes 1 through a table. So what do I get? I get e to the x. So what is it that we just noticed? Wait a minute. The derivative of e to the x, y prime, ended up being what? E to the x again. So in fact, what we know is, by the way the definition of the number e is, so we just discovered something. We just discovered that the derivative of e to the x gives me e to the x right back. So before we actually go ahead and give the derivative of e to the x, let me kind of define the number e. So the definition of the number e is the following. We know that e is the number such that limit as h approaches 0 of e to the h minus 1 over h, that equals to 1. So what does this help me do? This helps me kind of finish off what the derivative of e to the x is. So we can say that the derivative of the natural exponent function is given as follows. The derivative with respect to x of e to the x is going to be e to the x. So this we actually just proved earlier. Okay, we proved it up here, if you remember. So what's the nice result? And see, I keep telling you how I love to work with natural log and base e. How come? Because look, the derivative of e to the x is just simply e to the x. It doesn't get any better than that. So later on, we will also talk about, well, what if I'm finding the derivative of, let's say, 2 to the x? What if my base isn't e? And we also have formulas for those as well, but we're not going to talk about them today. We will talk about them in later sections to come. In fact, I think it's either next section or the second section after that. So for example 2, I would want you to kind of pause this video, and I want you to find the derivative of this function on your own, and then you could play the video and listen to what the solution is. So I want you to find the derivative of f of x equals to 5x to the 4th minus 3x cubed plus 17 square root of x plus 2e to the x. So take a minute, pause the video, and try to find this yourself. And once you're done, then play it and listen to what I have to say. So coming back to this, to find the derivative of this, remember the hint I gave you. Anytime we see any square roots or any kind of roots, write them in terms of its powers, because then I could use the power rule. So before I find the derivative, this will be 5x to the 4th minus 3x cubed plus 17x to the 1/2 plus 2e to the x. Okay, so now let's find the derivatives. Now remember, the constants are kind of just tagging along. So I don't really care much for the constants. It's just when I use the power rule, whenever I bring this 4 down, I'm going to multiply it to the 5. So the derivative of this, f prime of x, will be 4 times, bring the 4 down, so it'll be 4 times 5, which makes it 20x, and don't forget to subtract 1 from the 4, which gives me cubed. And then minus, bring the 3 down, so with this negative 3, so 3 times negative 3 will be negative 9x squared, plus, now bring the 1/2 down, times the 17 will give me 17 over 2x, subtract 1 from this 1/2, which gives me a negative 1/2, plus, now what's the derivative of e to the x? We just talked about it. It's very nice. It's just e to the x. So the 2 tags along, so it'll be just 2 e to the x. And there you have it. We just found the derivative of f. So if you look at this, notice how the coefficients, or these constants, just tagged along. I just found the derivative of each of these separately, and then I multiplied the coefficients that they had, which gave me the derivative here. Okay, so this basically finishes off this section. Like I said, we will talk about the other types of exponential derivatives exponential functions that we're finding the derivatives of. But right now, the only exponential function that you know how to find a derivative of is the one that has the natural, it's the natural exponent function, where it has e as its base, which, remember, the derivative of e to the x is always e to the x. So it's a really, really nice result. Okay, so that pretty much takes care of this section.